So I'm Dave Holland. I'm here to talk about a study that we did recently about using Flash for caching on the client side of a storage system. So today, up to now, Flash is used in enterprise and large storage systems, mostly on the server side, either in or in front of disks and file servers. We wanted to look at the client side, that is to say on the near side of a network, where the access latency can be much lower. This gives us the architecture you see here. We have a meat grinder, an application that talks to the operating system's buffer cache, which is RAM. This is a few gigabytes. And then under that, we insert a flash cache, which is larger, a few dozen gigabytes. That talks from the network to a file server. This basic configuration matches a number of things that happen in real life, like compute nodes and clusters, web application servers, nodes and render farms, and stuff like that. So the advantages the obvious advantages we're looking here for are to reduce the access latency and also reduce the load in the filer. So it turns out when you go to look at doing this, there are a lot of design questions that come up. So some of the things you run into. First question is, can the flash be write through? So for consistency reasons, it's desirable for the flash to be write through. Otherwise, you can accumulate large numbers of dirty blocks in your cache that you have to figure out how to get rid of or access remotely or whatever. But on the other hand, write through caches usually don't perform so well. So the question is, how much are you going to pay for making your flash cache write through? Next question is how tightly you have to integrate the flash cache. So if you have to integrate it with the operating system's buffer manager, then you have a nice complicated kernel hacking project that's going to be rather expensive. Whereas if you can just stick it in as another layer of cache underneath the operating system, then you could probably write it as a device driver, and it's comparatively easy. And then there's a question whether the cache needs to be recoverable. So flash is persistent, but if you want the whole cache to actually survive a crash, you need the cache metadata to be stored in the flash as well as the cache data itself. This increases the overhead. On the other hand, it means you don't have to fill the cache when you reboot, which for large caches can be a problem. And then there's a question, even if you make the flash cache write through, you still have to deal with invalidating blocks that have been written elsewhere. And given that making the cache is much larger, that can itself be a problem. So rather than latching onto a single point in this design space and hoping it would work, or worse, trying to build a system that let us try all these things, we went and wrote a simulator. So we went and validated the simulator against a client-side flash cache product from NetApp called Mercury. We validated our simulator against that to see if it was producing answers with the right order of magnitude. We did the validation with real traces, but our results, the graphs that I'm going to show you in the paper, are from generated traces, and there are a number of reasons for using generated traces, some of which many people are familiar with. The other reason is to be able to control the workload properties. There are also, in a simulator, there are a whole bunch of knobs you can fiddle with for controlling the way the cache is actually set up. First and most obvious, there's the sizes. So our baseline configuration is 8 gigs of RAM and 64 gigs of flash, which is not a particularly big flash, but it is big enough to give a good idea. We went to some larger ones and tried some smaller ones too. Then there's the writeback policy. So as I was saying, it'd be nice to figure out what happens if the flash is write through. So we tried 4 families of policies. Synchronous write through is where you write to the cache and then you write to the next layer down, you wait for it all to finish. Asynchronous write through is where you start the write immediately but don't wait for it. In A periodic model with a writeback cache. You have a syncer that runs in the background. We just run it periodically with any of a few periods. And the fourth policy is none, which is to say you just let the cache fill and evict only when you run out of space. These are pretty basic, but as we'll see, this was enough to do the study. There's also the architecture. The architecture is the way the caches fit together. We implemented three, which are called naive, look-aside, and unified. The naive architecture is the simplest possible thing. We just stick another cache underneath. So the application, which is off the top of this slide, writes to the RAM, RAM writes to the flash writes back to the file server. The look-aside model, which is what NetApp Mercury this is the NetApp Mercury design. The application writes to the RAM. The RAM cache writes back first to the file server, and only then into flash. This guarantees there are never dirty blocks in flash and has some other positive properties. But it more or less bakes in the synchronous nature, or the write-through nature. Reads can be serviced either from the cache or from the file server. Blocks that are read from the file server are written into the flash. These two models are actually almost identical. They differ only in some details, and they perform almost exactly the same. Then we have the unified model where we have one cache. The difference here is that in the others, we make no attempt to avoid duplicating blocks in RAM in the flash. The unified cache is a single cache that every block appears only once. The upside of this is that it uses your space more efficiently. The downside is that this is where you have to go and do a kernel hacking project. There's also stuff that we fiddle with at the hardware level, filer read ahead performance, which is to say the probability that if you ask the filer for a block, that it will already have it in its own cache, plus the hardware timings. We tried a bunch of flash timings because in our experience, every flash device or every model of flash device is completely different. We also had a whole bunch of knobs in our trace generator, which I'm not going to talk about in detail because the slides I'm going to show mostly don't reflect these. The one thing to note is that by default we chose to use 30% writes. This is somewhat arbitrary but seemed reasonable. And our default working set sizes are 1680 gigabytes, which is sized to both fit and not fit in the flash. We tried much smaller and much larger working sets and various values of all these things. So rather than go through all the knobs and all the data analysis, since that wouldn't fit in a journal-sized paper, let alone a talk, I'm just going to go through our headline results, which are basically the answers to these questions. First is the question whether the flash cache is a win at all. First time I gave a talk on this project, I left this point off and the audience wasn't amused. Then there's the question I mentioned of the writeback policy. Can the flash cache be write through? Then is the naive architecture good enough? As I already discussed that a little bit too. Then there's the question, does the cache need to be persistent? And what happens with cache consistency? And any other results we might have run across the way. So the first result is yes, the flash cache is a win. It's actually a fairly substantial win. So this graph shows latency on the y-axis. That's the read latency seen by applications. So the line at the top with no flash is bad. There are two things to note here. One is that on the left, towards the bottom, you see the performance is good as long as you fit in the cache. If you don't have a flash, then you fall into a really bad performance regime right away. If you have a large flash cache, you can stay in a nearly as good performance regime for much, much larger workloads. The other thing to note is on the right edge, where the workload is 5 to 10 times the size of the flash, you still get a substantial benefit. So this is a nice fairly large win. Second result is it turns out the writeback policy really doesn't matter at all. So this graph is a little hard to read at first because it's got 3 layers in it. The 3 layers are the architectures. I'm going to get back to that in a moment. The x-axes are the policies. So we have, on the left, we have the synchronous writeback from RAM, which, as you might expect, doesn't do very well. On the far right, we have no writeback from RAM, so we end up doing synchronous evictions from RAM, and that's slow too. But everything in the middle, you notice, is exactly the same. So that goes for effectively all the flash policies. For any of the RAM policies as well. Basically, as long as you do anything remotely reasonable, the performance will be basically the same. This means that, yes, the flash cache can be right through, which is good for consistency. On the other hand, if you have non-shared data, and if you make your cache persistent so you don't lose data, you can also set the writeback policy to something like, asynchronous writeback, or not async, periodic writeback of, like, say, 6 hours or something. And it will still perform basically the same, except that it will reduce the load in the filer. Now, as for the layers, you'll see that the unified architecture performs worse. This is because, in fact, it's entirely because the unified architecture is 8/9 flash, and so what you see there is 8/9 the latency, the write latency of the flash device. Unified architecture has no advantage. If you actually implemented a unified architecture for real, you would probably hide that latency. But we didn't because it isn't worth it. It turns out the naive architecture is just fine too. This is the read latency for the same family of workloads and settings. The naive is slightly faster than look-aside because of the difference in the initial. The naive doesn't do the initial write to the. Actually, that's not it. The naive reads into the. The naive reads into the flash slightly differently. It's very minor, not really very important. The unified architecture is faster. Here, this turns out to be, as we found in the details in the paper, we found by fiddling with stuff that this benefit is entirely because the cache is larger. So the effective size of the unified cache is 1 part in 8 larger. So what this means actually is that you can get this small benefit, but you could go do a lot of kernel hacking and get the small benefit, or you can buy a flash that's twice as big and get a much bigger benefit, which seems like a pretty easy trade-off to me. As for persistency, so this graph shows the application read latency, and the bottom line is with a warmed flash, like all the other graphs. The middle line, well, the top line is no flash. And the middle line is the flash, but without warming it first. So we normally run our traces to use the first half to warm the cache and the second half to measure on. For that line, we threw away the first half and measured on it, starting with an empty flash. So the flash then has to fill, and this takes a while and gets you really low latencies and so forth. And the reason that the lines converge is that on the right, the run length of the workloads is pegged to the working set size. So the workload on the right, which is 640 gig working set, runs for quite a while and basically fills the cache fairly quickly relative to its overall length. And so the performance is basically the same, whereas on the left, the smallest workload is 5 gigabytes, and it doesn't even begin to fill the cache before it finishes. But the takeaway from this is, and I should note that the runtime, to the extent this means anything, because these are similar virtual times, and none of the timings, the exact elapsed times are necessarily all that meaningful. But the fill times we're talking about here range from like 10 minutes for the small workloads to over a day for the huge one. The takeaway from this slide is that even the unwarmed cache, flash cache, is still quite a bit better than not having it. But it looks worth implementing persistence. And it turns out the overhead of persistence is zero. Everything, you end up having to do more writes to the flash, but this ends up hidden entirely behind the RAM cache. And as far as consistency, so this graph shows the percentage of writes done by application that cause an invalidation. So this is two hosts sharing the same working set, so it's a fairly adverse workload. But you'll notice that even for the small workloads, the invalidation rate is much higher with the flash than without. So greater than 90% for the workloads that fit in flash. And I should note this is in some sense a preliminary number. We did not implement a particular cache consistency protocol. We used simulator global knowledge to invalidate blocks. So this, and there are more graphs in the paper, reflect the overhead caused by having to reload blocks, but not the overhead caused by cache consistency traffic. That said, 90% invalidations is substantial, and this is something that merits further investigation and a detailed study modeling some real cache consistency protocol to make sure that to find out whether it's going to cause scaling problems or other issues. And I mentioned another result. And so it turned out that if you have a nice big flash cache, for at least some workloads, using RAM for caching as well isn't worthwhile. So in this graph, we have both read and write latencies. The write latency is on the left and the bottom, and the read latency is on the right and the top lines. The red line at the bottom is a artifact caused by the RAM cache's sinker getting behind. So if you use a periodic sinker, before I get into that, I should state that what we have here is different RAM sizes ranging from 8 gigs on the right all the way down to 0. So it turns out if you use the small, really small RAM sizes and you use a periodic sinker for the RAM cache, it gets behind and you start doing synchronous evictions. This is not very interesting. If you fix that, which is the blue line at the bottom, you can go all the way down to 256K of RAM before you start seeing write penalties. That's basically just enough RAM to do write buffering. If you look at the read latency line at the top, you see at the right, if you use 8 gigs of RAM for caching as opposed to 0, there's a slight benefit that's like 2%. And that is almost certainly not worthwhile. 8 gigs of RAM across a cluster can still cost quite a bit of money. You almost certainly find better use for either the RAM or the money. Now, some of you may be thinking this is obvious because this workload doesn't come in close to fitting 8 gigs of RAM, which is true. But it turns out that even for workloads that do fit in the RAM, the penalty is not very large. So here we have 5 gigabytes of RAM, so it fits completely in the cache for the rightmost point. The penalty there is 25 to 30%. Now, 25 to 30% penalty on access read latency, it's maybe substantial. It might not be something you want to pay. On the other hand, for some workloads, it might be something you would be willing to pay if using that 8 gigs of RAM for your application has other larger benefits. And I should point out that this is entirely possible because of the flash cache. Without the flash cache, the penalty of trying to do this, doing without RAM for caching, is it becomes 5 times slower. which is a complete non-starter. So I have, this is in some sense a preliminary result because this may not apply to all workloads, et cetera, et cetera. But it's something worth thinking about, something worth considering, possibly looking at in real systems. The cause basically is that the application read latency is dominated by file remisses. That is to say, you go to the file server, it has to go to disk, because that takes milliseconds. And the large flash cache cuts down the number of those, and and overall, it has what we consider a fairly surprising effect. But again, this probably only applies to some workloads. So in conclusion, client-side flash caches are a pretty big win. It's okay for the cache to be write through. The cache does not need to be integrated with the file system. Persistence is not necessary, but it seems worthwhile, particularly if you have a client that crashes a lot. So if you're using Win98 in your clients, you might want to consider persistence mandatory. And there's some consistency issues that remain open with, for shared data. We really started out looking at SAN-type disk images, and so we did not get to that in as much detail as we might have liked. That's that. Here are email addresses if you want to contact us, and questions.
Michael Condit, NetApp. When you're talking about it's okay for the cache to be write through, this is under the assumption, as I understand it, that the RAM is using a write-back cache strategy, and therefore it's acting as a buffer. It's buffering up writes, yes. and the application is not being forced to wait for the write-through of the flash cache.
If you set the RAM to be set the RAM cache to be synchronous,
yep.
You get the horrible behavior at the far left of this graph.
Right. Now, but another interesting question, which I don't think you addressed, is what if as with most serious enterprise applications, the application is insisting on synchronous writes. Can the flash, therefore there will be essentially no write caching. There'll be no performance benefit from the flash cache if it does a write through. Is there any way that you can use a write back policy in the flash cache to accelerate those writes? Just as an example, one of the startups doing a host-side flash cache has decided it's okay to do a write-back policy in the flash cache for those synchronous writes as long as you replicate the data to a peer host-side flash, another flash cache on the client side somewhere else in the network. Now you have two copies, and that's enough reliability.
That would work, I think, yes.
Nice observations. I was just wondering if the observations or the effectiveness of the cache, to what extent it would change if you have a skew in the workload, like if it's a heavy-tailed read or heavy-tailed write distribution. That's
so actually, I didn't really mention this because I didn't want to go too much into the workload parameters. But one of the knobs in our trace generator was the fraction of I/O that is taken outside the working set. We picked 20% because it seemed reasonable, and there didn't seem to be a whole lot of reason to change it after looking at the sensitivity. The sensitivity of that is not that high. One of the advantages of the big flash cache is that it does sop up a significant fraction of the of those I/Os. It's the substantial benefit of the flash is that it's large.